Okay, so in this video we are going to tackle the concept of independent random variables in the context of continuous random variables. Recall from an earlier video that the definition of independence for discrete random variables, so if I just write the title, independent random variables. Okay, so in the case of discrete random variables, we said that a random variable is going to be, two random variables were going to be independent. And I'll just quickly remind you of the setup. We have our abstract probability space here, and then we have two random variables defined on this. So we have a random variable x and a random variable y, which are each basically mapping every single outcome in each of these probability spaces onto a number, onto a real number. And of course, we then let this standard probability space, where the outcomes are real numbers, adopt or inherit the probability space structure of here. We let every event in here have an event back here, and we let the probability of these events in here be the same as the probability of the preimage of those events in here. Okay, if we take basically because any event in here, so let's say we have an event in here, let's say this is an event here, and let's say we've got an event in here as well, which we'll call A. Then we have the preimage of E in here, which is x inverse of E, and we have the preimage of A potentially, and they potentially overlap, and we have the preimage of A. Because this is a sigma algebra, because since F is a sigma algebra of subsets, it implies that if x inverse of E and y inverse of A are both elements of F, it implies that their intersection, x inverse of E intersect y inverse of A, is an element of F, which means we can ascribe a probability to it. So if we take the probability of x inverse of E intersect y inverse of A, then we say that the random variables are independent if this is equal to the probability of x inverse of E times the probability of y inverse of A. So basically, it's exactly the same definition as for two events being independent, but basically what it's saying is take any event in here and take any event in here, take their preimages, which are events in here, and those preimages of these events have to be independent no matter what E and A you started with. For all E is an element of, let's call this this F prime, so this is the probability space omega prime, F prime and P prime, and we'll call this one omega double prime, F double prime and P double prime. So for all E is an element of F double prime and A is an element of F double prime. So this is F prime rather than F double prime. Okay, so basically take any event in either of these probability spaces, take their preimages, and the intersection is also an event, and the probability of that intersection has to be equal to the probability of each of the two events multiplied together. So basically the preimages of events have to be independent for every event E and every event A you pick in your standard probability spaces. Okay, so now let's. So what we then said is, events in discrete random variables are just unions of the sets containing single outcomes. So if we make this is true, if this statement is true for all singleton sets and singleton sets Y, which is the singleton sets in here. So if you take single outcomes in here, x and y, put them into sets by themselves, and if this statement here is true for all x and y, i.e. the probability of x inverse of this singleton set containing x intersect y inverse of this singleton set containing y is equal to the probability of x inverse of x times the probability of y inverse of the singleton containing y for all singletons, then it's going to be true for all sets, and you can show that simply because every set you can take, every event is just going to be a countable union of these, and then you'll just use the second axiom of probability spaces. Okay, but what is the probability of x inverse of x? That's just equal to the probability that x is equal to little x, and this is just equal to the probability that y is equal to little y. And this overall here, this big thing, is just equal to the probability that x is equal to x and y is equal to y. So that is the statement that we had for discrete random variables. We had the statement that the probability that x is equal to x and y is equal to y is equal to the probability that x is equal to x times the probability that y is equal to y for all x and y, for all x is an element of this probability space up here, so all x is an element of omega prime and y is an element of omega double prime. Okay, so that was our definition for discrete random variables. For continuous random variables, these are no longer, these are events, these singletons are events, but their probability is 0. So that's not particularly interesting. Those aren't particularly it wouldn't make a particularly interesting definition to use this as our definition. Okay, so instead what we say is we look at different events. We basically, for discrete random variables, if you can say you can build all events from the singletons, from these events containing the singletons. In the case of continuous random variables, as we've seen, you can build all events from the event that x is less than or equal to little x and y is less than or equal to little y for all x is an element of omega prime and y is an element of omega double prime. So basically, these become your new events. The event the set containing all outcomes which map onto a value less than y. That becomes a set. So if I wanted to rigorotize this, I'd write the set of outcomes. So S is an element of omega, such that x of S is less than or equal to little x. That becomes an event, and S is an element of omega such that y of little s is less than or equal to little y. Those become events. And if you have all of the events for every possible x and every possible y in these images here, but of course you can define this for the entire real numbers, then basically you can build all other events out of these. So if it's true for these, in the similar way to the way it was true for the discrete case, if it was true for all of the singletons, if it's true for all of these, it will be true for all events. So we therefore define for continuous random variables, the independence property is that the probability that x is less than or equal to little x and y is less than or equal to little y is equal to the probability that x is less than or equal to little x times the probability that y is less than or equal to little y. And basically we're just applying this formula for the events. The events that we are putting in here are the events that x is less than or equal to little x and that y is less than or equal to little y. So that becomes the concept of independence for continuous random variables. And I just want to also